Why it just magically disappeared, I have no clue. I have had that happen before on this machine. I don't know why. It's only on this machine. It never does it on any of my other machines. Okay, so that said, okay, so let's just do a little sketch about what we did yesterday because I don't want to be entirely talking about that. So last time we derived PV equals NOT. You're not responsible for that derivation, but I do want you to know where it came from. And so what did we do? Let's just do a brief sketch so we can see it's really not that hard. So what did we do? We said here was a wall. We said a molecule is coming this way. This is some V. So this is Vx. This is Vy. It comes here, it ricochets. Like that. So here's minus Vx and Vy. We said the reason it ricochets is that at this point here, there's going to be a force that the wall exerts on the molecule. We're going to look at the average here. So these are all, this is an average velocity here that we're dealing with. These are all average quantities. We did the force impulse momentum relation. We said that the average force here, in the x direction, okay, the net force, well, let's say net, average force here, times dt has to equal the change in momentum of this guy here. So we said it was this minus mvx, minus mvx here like this. So this is our minus 2 mvx. We divided through by this delta x here. This was the average force in the x direction that the wall puts on the molecule. Okay, there is So then, what did we then do after that? Number of molecules. So we said if we wanted the average number of if we wanted the average number of the average force on here, we'd have to multiply this by the number of molecules here. So if you want the total force, average force that the wall exerts on the molecule, it's be this n times 2 mvx over delta x. So that was that total force. Now how did we convert that into a pressure? Yeah, we said pressure is force over area. So what, and also what did we say? We said if we want if we want the actual force that the molecule puts on the wall, so the wall is the opposite of this. So we said that the pressure, so we made the force that in the x direction here, average, that the molecule puts on the wall over the area. So that's going to be this guy here. And what did we do? We multiply the top and bottom here by the x and by 2. What did we say about this fellow right here? We said this was 1/2 m vx squared. That's the average kinetic energy in the x direction. We said by the equal partition of energy theorem, it has to be as what else? 1/2 kBt. So that allows us to write this as n. Here's a 2, I'll put the 2 here. 1/2 kBt. There's another 2, so I'll actually make that 4 over a delta t dx. We need to know a way of figuring out what that is. What did we say? What was our estimation for that collision time? And this was the fake part. We said here's our box. And this is L. What did we say was our estimation for that contact time? Yeah, we said the time it takes for a molecule here, traveling at Vx to go this way and then back, that's going to be what that delta T is. Okay, which is fake, but that's what it is. So we said the distance traveled is 2L, the velocity is Vx, the time is delta t. So this delta t is 2L over Vx. We took that, put it in here. That 2 cancels that 2, or cancels one of the 2. So we get this A, 2L, Vx, Vx. Those Vx's cancel, that 2 cancels. A times V is, I'm sorry, A times L is the volume. So that gave us the pressure is N kVt over V. And so this gives us PV equals N kVt. This right here is how, if you ask a physicist for the ideal gas law, they'll always give you this. This is how you write it in physics. This is the ideal gas law as a physicist writes it. Okay. How do we get it in terms of the chemist? Yeah, we said the number of moles is the number of molecules over Avogadro's number. This N is this N and A. We put this in here. And this is what? This is our R. This is our NRT. Okay. So there's a reason for this. Yes?
So like back in the one step up, how do they know to multiply it by Vx over Vx and 2? Like where do that?
Okay, which part am I doing?
Yeah, like on the right side of the equation. Like what? How do they?
Well, you want to get it, because if you leave it like this guy here, you're thinking, you know, what's Vx? And so if you do know about the equalization, then you do. Meaning you have to get the kinetic gas. Okay. So you have an M here, you have a Vx. If you had another 1/2 of Vx, you have kinetic energy. That's what you get. But also, it's just not one day people decided this. I mean, it took a long time to come up with it. You know, there's a lot of thought. I mean, you're seeing the aftermath of somebody figuring it out. Yeah. Once somebody figures it out, it's easy. But it's that first person to figure it out, that's hard. Okay? So what we want to do is we want to look at basically, we want to start looking at graphs of P and V and ask what we can start doing with those graphs. Yeah, you're not responsible for that derivation, but it's just always good to know where something comes from. The van der Waals equation of state, which is a very, have you seen the van der Waals equation of state? Maybe I'll show it to you later on. It's the first correction to this one here. It's for more realistic gases. So what we could do is we could say, what does, let's consider an ideal gas in a cylinder, let's say in a piston, okay, and look at, I'll look at the PV diagram. So here's our little piston. Right here. So here's our little gas. And we can compress this, so we can push down on this with the gas and expand up on it. So we have a different volume. So this is some volume. Okay. And so what we're going to do, we're going to look at the pressure of the gas versus the volume. Okay. So first of all, if we had one point here, I'd have the pressure of the gas, I'd have the volume of the gas, there'd also be some temperature here too, as well. So one point in here corresponds to basically a P, a V, and a T. Where would the T come from?
The faster the molecules are moving around in that compressed space, the higher the temperature.
That's true. Let me rephrase that, mathematically. What if I give you a P, if I gave you a V, you know there has to be a T? Yes, exactly. You know from PV equals nRT. If you have P, if you have V, so that's the point on that graph. That automatically implies the temperature. Does that make sense? So let's assume that the T doesn't change. So look at constant T. So nRT here is all constant. So we have PV, we have P equals nRT over V. So this is really a constant. So what happens if you plot 1 over a variable? It goes like this. So you're going to get a line that goes like this. Let's do a little more curve. Like this. This is an isoform. T is constant all the way along there. What would the gas be doing here? Let's say the gas is moving this way. What would the gas in this piston be doing? They'd be expanding that piston, right? You can see the volume is increasing. So that would be the gas actually expanding it. If you compress it, what would it do? You're going like this, and then you're going down along there, if you go along an isoform. That make sense?
Wait, so that curve we're looking at right now is if we're compressing this.
It depends on what you do. You can go this way with it, or you can go this way. And again, we're assuming that the temperature is staying the same. It's not always going to be. We're saying that if you keep the temperature the same, you can either expand the gas along here, or you can compress the gas. So this would be expansion. If I make the air going like this, that would be compression. Okay. Now we said that this is for some temperature. I'm going to call this T1. So this is T1. How do we say this? If we increase the temperature, how do the different isotherms look? So if we increase this constant, so I have a bigger constant over the volume, how does that look?
It's the same, but
This is higher. Okay. So you're going to have something like this. So this would be some temperature T2, where T2 is greater than T1. Give me another isotherm. So this would be T3 equal to T2, and so on and so forth. So this all has T1, this all has T2, this all has T3, this all has T4. Yes.
I kind of blanked. So like the T2s and the T1 is if like the temperature was not constant.
No, they're all going to be constant, but here I'm looking at just a constant value of T1. Now I'm going to look at a constant value of T2, so I change the temperature, a constant. That would be in this upper graph here. And then I'm going to make it higher again. So if I keep my temperature constant here, then this is one here. So these are all isotherms. Okay. Now we can look at something also called an isobar. So what's an isobar?
be kind of similar, just like bars.
Well, the iso is going to be equal. Okay. The bar, that's used for what kind of quantity? What part of the gas? Pressure. Think about when you listen to a meteorologist, they talk about barometric pressure. Get the word bar in there. So this is going to be, what do you think that so an isopressure process is going to look like? What? That's going to be a straight line. So an isobar is going to be this. That would be an isobar. Would that be a compression or an expansion?
I mean, it's not doing.
Well, I'm going this way here like this.
Oh, that would be expansion.
That'd be an expansion because the volume is increasing. If we're going this way, then it'd be a compression. If the gas expands like this, is that going to heat up or cool off, or what's it going to do? What would happen in a case like that? Would that gas heat up or cool off?
Oh, which one?
This one. How do isotherms look? Isotherms look like this. Is it heating up or cooling off? It's heating up. Remember, this is lower temperature, higher temperature. If you're going like this, you're cutting isotherms. Okay. So to keep the pressure constant while the volume expands, the temperature of that gas is going to have to heat up.
Dr. Laux, can you repeat that? I did not hear you.
Okay, so the question is, if you have an isobaric process and the gas expands, does it heat up or cool off? And look at the isobars. The isobars look like this. So you're going from a lower one to a higher one. They also have something like this. You have an isochloric process. Okay, what is that one? What else do you think we could keep constant? Volume. So this an isochloric also means isovolumetric. That'd be something like this. Isochloric.
Like above it.
So for the isobar, the volume stays constant, you said, right?
No, for the isobaric, the pressure stays constant.
Oh, okay, okay.
Okay. So let's look at. And remember me good. Okay, speak me really well. You speak goodly. Okay. No, you see me write something incoherent like that, call me on it. Okay. Although I think bad grammar is fun, so I don't mind bad grammar. Okay? I'm writing a whole book of bad grammar. Editor, hard time, read not good. Bad editor, bad. Bad editor, bad. Grammar not good. Okay, so does this heat up or cool off? If I were to do this one, how come? Because my isotherms look like this. We know that these all correspond to higher temperatures. So if we go like this, I'm cutting these isotherms. Okay. So I actually got hotter. Okay. Okay. Now, why do we worry about this? Because this is why we worry about this. Let's ask, what happens? So why do we worry about these processes? Because what it's going to do is that we can add heat to a gas. Let's say when we add. When we add heat to a gas, the gas can do several things. Its internal energy can change. But it can also do work. What we can do, we can add heat and do work on the system kind of in an isobaric fashion or an isoporic fashion or an isothermal fashion. We can do a lot of things on the gas, we can't follow those curves. We do that, it's going to correspond to dumping energy into the system, or having the system do work. It's going to correspond to different things we make the gas do. So, as the gas expands or is compressed, it can often follow isobaric, isochloric, or isothermal. You can take any path you want, but these are going to be common ones you do. And so all we want to do is ask, how do we do this? So how can we describe how the system changes? When we add energy and or the system does work. That's what we want to look at. And this is all the basis of what's called the first law of thermodynamics. So answering this question, is the first law of thermodynamics. The first law of thermodynamics is really a conservation of energy law. Yep.
On the right, what is that for the second? Second line, yeah, what is that?
Compressed. Okay, so the first law of thermodynamics is conservation of energy. So let's see how we can do this. So, how can we change the internal energy of the system? Okay, so what's the symbol for internal energy? We haven't used it in a little bit. We used it on Monday. Okay, it's going to be U is the internal energy. So we want to ask, what is delta U? How can we change that? And what does internal energy measure? Take a gas. So what does the internal energy measure in a gas? And what's that connected with? That's perfect. Okay, it is, but the motion is always called kinetic energy. So if you look at the kinetic energy of the gas molecules moving all around, that's the internal energy. So we want to ask, how can we change that? So give me a dumb way to change it. What's a dumb way to change internal energy? What can I add to the system? You don't really add pressure. heat. I can add heat to the system. Okay. So one thing I can do is I can just add my delta Q. If I add heat here, that's going to go to changing the internal energy of the system. That make sense? Well, let's go back and look at our piston. So I can dump in some delta Q here. What can that do? That can make the molecules move together, move around a lot faster because I'm dumping in heat. What would that gas do to that piston? I might push it up, so it's doing work on it. If this gas expands and does work on this piston, is that taking away energy or adding energy? If it does work. It's taking it away. So I can just as I have to also subtract any work done on the system. So this is energy you're adding to the system. And then this is work being done in the system. And this right here, in this form here, this is your first law. Okay. So how can you change the internal energy of a gas? You dump in heat, or you remove heat. If I remove heat, is what value is it? Negative. So I make this go down. And also, if that system expands, if the system does work, that's positive. That would lower this energy. So if the system does work, the W is greater than 0. If work is done on the system, how would I do work on the system? You take that piston, and I can actually push it down. Okay. So, but if work is done on the system, delta W is less than 0. And that adds energy to the system. Make sense?
How do you know the difference between doing work and work?
Okay, so how do you tell? Okay, let's go back to this case here. If the system did work, what's happening, the piston is pushing up like this. What would we call that? That gas is going like this. We call that expansion, right? So if this gas expands, it's doing work. So this would be positive. But if I compress that gas, if I put my hands on there and then go like this and compress it, then what am I doing? The volume is getting smaller. So a compression would be an example of doing work on the system. Make sense? Good. Let's take an example. We need one other thing. Actually, do I want to do that one there? Because that's going to twist your mind around for the file. Let's do one other thing. Then we'll okay. Let's ask, how can we find work done on a system? Okay. And to tell you how this goes, okay, the claim is, the answer, the area under the PV diagram in the PV diagram is the work done on the system. So I want to prove that. The proof is actually kind of simple. What I mean here is if you look at this, if this is P, this is V. Here's your initial spot. Let's see, here's your first spot. Here's your second spot. Let's say I have some curve that looks like that. Who knows what that curve looks like? Doesn't matter. If I look at this area here, this area under the curve, is delta W. I'm going to prove this. Okay. That's going to be a nice thing to do. So let's prove that. Okay, so this has an area here. We have some gas in here. There's some pressure P here. What's the formal definition of pressure? Force on a certain spot per unit. Area. So if I know the pressure of this gas, if I want to find the force on that piston, I take PA over here. That's the force on that piston. So this is the force the gas exerts on that piston. Now let's say that that piston moves up some little distance up to here. So let's say this gas moves up some little tiny distance delta X. It's small. What is the definition of work from first semester physics?
Like negative delta U or delta U.
That's true, okay, with a conservative work. What else? Just more generically. What is work? Force times the distance. So if I want the tiny amount of work done, on this thing, what do? I take the force, this F, times the distance that piston moves, delta X. Well, what is my force? My force is the pressure times the area. What is A times delta X? What would that be? Time delay. Yeah, volume. Right? That actually be the change in the volume, right? This is A, this is X, so this gas is changing by this much volume here. Right? So this is really your P times your change in volume. Let's see graphically what that means. So here's my P diagram, PV diagram. We said this gas is starting here and it's going like this. So what am I going to do? I'm going to take the pressure here, And then that volume basically changes by this amount. So this amount right here, this is my change in volume. Graphically, what is this pressure here times delta V? So take the pressure here, at this value, times V, what is that combination? This is the area of this little section here. So this little section here, right? The area here is P times delta V, but that's nothing but the amount of work done on that piston. So now my piston is here. Then what happens? It expands a little bit more to here. So now it expands some little distance here. So what do I do? I take the pressure at this point, times this area, and this little delta W is going to be the pressure times delta V. And what's going to happen is it keeps on going out like this. Okay, I'm going to take this little rectangle plus this little rectangle plus this little rectangle plus this little rectangle. I'm going to add up all these little rectangles here, the areas here. Well, if I add up all the areas of these little rectangles here, that's my total work done. And that's the area under the curve. That make sense?
I know you're not supposed to do calculus, but would you just do it?
That's what you do. But since it's not calculus, I didn't do it that way. But that's all it is. Just the integral of the curve. But it comes from this argument. Right? So if you wanted to kind of do the same thing, you'd say the total work, the sum of all these P times delta X's here, you use P times delta V's here. Because you're summing them all up. Then you take the limit as delta V goes to 0, which means that you have a rerun sum. Well, you have a rerun sum here, but when you take the limit as delta V goes to 0, the rerun sum becomes an interval. But that made no sense to over that. Okay? So this is why it's the area under the curve. Okay. So let's take an example here. Let's say we have a gas starting here. Okay, we're going to measure okay, so what are the units for pressure? Okay, so it's going to be a Newton per meter squared. And a Newton per meter squared is by definition 1 Pascal. Okay, so we're going to measure this in pascals. What do the chemists use? They frequently use atmospheres.
Oh,
So often they'll have atmospheres here. There's a bazillion pressure units. You start getting millimeters of mercury and all this other stuff, and inches of mercury. And we're going to use MKS units. It's always going to be Pascal. So let's say that this is, I'm just going to make up this value. I'm going to say it's going to be 200 pascals. So let's set the volume here. It's right there. And I'm going to measure the volume in terms of cubic meters. What would the chemist use? Liters. So they often might have atmospheres per liter. I mean, they wouldn't have to, but they do. So I'm just going to make up a value here. I'm going to say that this is Q. And this gas is going to expand this way to here. It's going to go up to 10. I want you to find delta U, delta W, and delta Q for this process. And we're going to say that we're going to assume we have 3 moles of helium. Okay. One of these is really, really easy.
delta W just 8 times 200?
Done. How come?
It's like the line.
Yeah, if you look at the area of this curve here. Okay, is what? It's gonna be the height here, 200. Times basically the width. So this is, 10 minus 2. So this is 200 times 8, or 1600. What would be the answer for this? Joules. Is that positive work or negative work? Did the gas do work, or was work done on the gas?
So it's expanding. Right?
It's expanding.
So in that case, work
Was
was done.
done by the gas because it's expanding. So this is positive because the gas is doing it. Okay. So that takes care of that one. Now, okay, just so you know, these are the problems that really don't stop. Just a little bit like slaying a dragon. If you read some of these, okay, The Lord of the Rings was written very brilliantly. The problem with it is that then everyone decided to have these quest books after this point. Most of the people writing these quest books, the quests are just not stopping. They're going on and on and on. It's just a bad quest. These problems become a little bit like a bad quest. They don't stop. Tell me how to find this and why we can actually find that. Why are we going to do that next? Sure. But we don't know delta Q. What is U again? Internal energy, which is connected with what? Kinetic energy. What kind of gas do we have? A monoatomic gas with how many degrees of freedom? Three. What are they?
Up, down, away, exponential.
Exactly. It can move this way, it can move this way, it can move this way. It's 3 degrees of freedom. What does an equal partition of energy theorem state? That for each degree of freedom, you have how much average kinetic energy? 1/2 kBT. Yeah. So there are 3 degrees of freedom. Okay. XY, motion in XYZ. So the kinetic energy. So if I want the average kinetic energy, one molecule, well, let's say 1/2. That's 3 times 1/2 kBT. How many molecules do we have? 10 of them. We have N molecules, or N atoms. If I want the total kinetic energy, which is nothing but the internal energy, that's all it is. Need this. This would be N times 3/2 kBT. Hey, but I don't want to have N. I have a number of moles. What will I do?
N equals.
Now, the little one, the number of moles is N over Avogadro's number. So our N is N little n NA. I think we have a friend. Which is what? Or NA times kB. So we end up with 3/2 nRT. How do I get a delta U now? All I have to do is find the change in the temperature. That's what we're going to have here. is delta U. Is then gonna be 3 halves NR delta T. So I need this temperature here. Here's my initial temperature. Here's my final temperature. And if I know that, I can calculate my change in temperature. How do I find those temperatures? Because I told you this is a class. Yes. What was this value, 200? So to find T, use PV RT. So P, so T. So T is PV over NR. Okay, so let's get T1.
What is R again?
What is R?
The value.
8.314. Okay. So our T is going to be what? T1 is going to be P, which is 200. Our V is 2. Our R, or N is 3 times 8.314. Does somebody work that out for me?
$16.
16 point what?
0 to 4.
I'm just going to 16. 16 point.
Question.
Yes.
Where did that 200 come from?
That was given. I told you that the initial pressure was 200.
Oh, okay, all right.
Okay, now let's find, so this is our initial. Tell me how to find T final. This should be 200 times 10 times 3 times 8.314. This is going to be 5 times greater. So this is going to be what, 80? How did we know that had to be a larger temperature? How do our isotherms look? Isotherms look like this. You can see you're cutting like this, so you had to be going to a higher temperature. These will get, the first time you see it, these are, they just don't stop. That Journey song, Don't Stop Believing, what it really was about was, never forget that when you do these problems, it will come to an end. It's a metaphor. It's a metaphor. I'm learning so much here. Okay, so tell me what delta U is. 3 halves N R delta T. So it is 3 halves times 3 times 8.314 times 80 minus 16 equals. We're going to use that in a second. So what do you get for this guy? There's no answer coming in from the start. 798 joules. Okay, have we dumped heat into the system or removed heat to do this? Most of my delta Q. Does energy come out of this? Or do I dump in energy? Okay, so we know that delta U is delta Q minus delta W. So delta Q is delta U plus delta W. So we end up with 798 plus 1600. Okay. So this is positive. So did we dump energy into this or did we pull energy out? It's positive, so heat was added to the system. How would this change if we had a diatomic molecule? Exactly. We do the same procedure, with the difference is that now we have 5 degrees of freedom. Okay? That,
He was removed, right?
no, he was added to it. We know that because it was positive.
Call it monatomic if it's three-way.
Well, it's monatomic because there's just one molecule. Okay? These problems will take a while. Okay, you just do one little thing, it's just a cascade of matter. Okay, enjoy your day.
Did you tell us if the molecule was
I would find it. Okay, although there's something like, if I said like O2 or M2, it should be.
We're gonna have homework on this tonight?
Yes, if I can find it. The book does not do any of this?